In this video, we will go through two examples of how to use the multiplication rule and the addition rule for computing probabilities. These rules are used to compute the probability of compound events, which is when we want to know the probability of two or more events happening. The multiplication formula is used to find the probability of one event occurring and another. The formula shown here tells us that if you want to find the probability of two events both occurring, let's call them events A and B, then you would want to take the probability of event A occurring and multiply it by the probability of event B occurring. This notation here with the straight line represents the word given. I would read the second part of this formula as the probability of B given A. What it means is that when you are computing the probability of event B, we will do that computation assuming that event A has occurred. And we will go into more detail through our example here. So for our example, we're going to draw two cards from a deck of 52 playing cards. And we want to find the probability that both cards we draw are aces. So there's two situations. The first situation is when we draw the cards with replacement. This means that we're going to pull the first card out of the deck and then put it back before we pull the second card out. So what we can do is call event A being that we have an ace on the first card, and event B is that we pull an ace on the second card. If I wanted to find the probability of drawing two aces, part of what I have to realize is that this is actually a succession of events where I have to pull an ace on the first card and an ace on the second card. If I think about these two events individually, the probability of event A, which is an ace on the first card, I could find by using the relative frequency. There are 4 aces in the deck out of 52 cards, so 4 out of 52 would be the probability. If I think about event B, an ace on the second card, what I really need to consider is the probability of event B given that event A did occur. But in this example, it actually has no effect on the probability. What happened on the first pull is not going to affect what happened on the second pull because I'm putting the card back. So if I put the first ace back, I will still then have 4 aces in the deck out of 52 total cards. So the probability I draw an ace on the second card is the same. It's 4 out of 52. To find the probability of both of these events occurring, I would need to multiply. So when I multiply these two values, I get a fraction that would be 16 over 2,704. Situation 2 will be when we draw the cards without replacement. What that means is that when we pull the first card out of the deck, we're not going to put it back. So computing the same probability as above, we want to find the probability of drawing two aces. So we'll call event A that we pull an ace on the first card, and event B that we pull an ace on the second card. Well, nothing's changed for the first card. The probability that I pull an ace on my first card would be 4 out of 52, just like before. But on our second pull, something's now different. Because I'm not putting the card back, I have a different probability for pulling an ace on the second card. Now what I have to do is I have to assume that the first event did happen. So when I compute the probability of getting an ace on the second card, I do it under the assumption that I did pull an ace on the first card. If that's the case, then there are only 3 aces left in the deck, and there would only be 51 cards left in the deck. So the probability of getting an ace on the second card, given an ace was pulled on the first card, would be 3 out of 51. Now using the multiplication rule, multiplying those two probabilities together, I get a slightly different answer. The key to finding these probabilities is always to assume that if you have compound events, always assume that the first event did occur. You might think, what happened if I didn't pull an ace on the first card? Wouldn't there still be 4 aces left in the deck? Well, yes, that is true, but when we compute the probabilities, we always assume that the first event did happen. Because if the first event didn't happen, if I didn't pull an ace, well then what I get on my second card would be irrelevant, because there would be no way for me to get aces on both cards. The second rule we want to go over today is the addition rule. The addition rule is used to compute the probability of one event occurring or another. The basic premise is that to find this probability, we need to add the probabilities of each of the separate events. And then we need to account for the fact that these probabilities might overlap by subtracting the probability they could occur together. So let's take a look at this formula with two different examples. In our first example, we're going to use our 52 cards, but this time we're only going to draw one card from the deck. And on that one card, I want to find the probability that is an ace or a king. So for this example, our event A will be that we pull an ace on the first card, and event B will be that we pull a king on the first card. So there's only one card being drawn. The probability of event A, similar to the last example, would be 4 out of 52. And the probability of event B, that I draw a king, is also 4 out of 52. And again, I'm using the relative frequencies here to find these probabilities. Now, there's no probability that I could draw an ace and a king at the same time. So these events are impossible to occur together. When events cannot occur at the same time, we refer to them as mutually exclusive. Mutually exclusive events have a probability of A and B equal to 0. So to finish our example, if I wanted the probability that I draw an ace on the first card or a king on the first card, I would simply add those probabilities together, giving me a result of 8 over 52, or 0.153. Let's go down to example 2. Again, I'm going to draw one card from the deck, but this time I want to calculate the probability it is an ace or a spade. For reference, there are, again, 4 aces in a deck. There are 13 of each suit in a deck of cards, so there are 13 spades. I'll refer to event A as pulling an ace, and I'll refer to event B as pulling a spade. Nothing changed on event A. The probability I draw an ace, there's 4 aces out of 52 cards, so 4 out of 52. The probability I'd pull a spade, since there's 13 of them, would be 13 out of 52. But in this example, our two events are not mutually exclusive. They can actually occur together. If you went into the deck of cards and you pulled out the ace of spades, well then you would be satisfying both event A and event B at the same time. So there is an overlap on these two probabilities. If I were to just add up all the cards that were aces and all the cards that were spades, you might think, well, there's 4 aces and 13 spades, so there should be 17 cards. But actually, if you calculate it that way, you're double counting the ace of spades. You counted it as one of the aces, and you counted it as one of the spades. So this overlapping probability has to be subtracted from my addition. So to do the formula, I would do the probability of A plus the probability of B, and then I would subtract the probability that they could occur together. And since there's one ace of spades, that probability would be 1 out of 52. That is how I end up with the result of 16 over 52 for this example.